Hey guys, and welcome back to a new Kotlin video. In this video, once and for all, the differences between threads, coroutines, dispatchers, concepts like concurrency, parallelism, those kinds of terms that Kotlin developers so often just completely mix. So after having watched this video, you will definitely understand what a thread is, what is blocking code, what is suspending code, what are the differences, what is concurrency, what is parallel code execution. You will understand things like why the I/O dispatcher is better for I/O calls, and you will learn about why the default dispatcher is better for things like CPU-heavy operations. In this video, it will all click for you. And in case you don't know me, I'm Philip, and I'm doing nothing else than Kotlin development since 2019. So if you want to learn to develop Kotlin software for the entire stack, then subscribe. So here we are in a completely blank Kotlin project, in which we want to start understanding what a thread is. Threading and threads in general are a concept that applies to pretty much every programming language out there, while coroutines is something that is not exclusive to Kotlin, but something that definitely does not exist in every programming language out there. So let's start with understanding what a thread really is. And for that, I will actually create a function here that we call blocking code. And in this function, we just want to simulate some kind of CPU-heavy thing, just some kind of code that takes a moment to complete. For example, iterating over the numbers from 1 to 50 million. And then maybe saying, okay, we map that to the square of each number. So we just calculate the squares of all numbers from 1 to 50 million. If we now execute that here, blocking code, and we maybe print something before, start, and print something afterwards, like end, and we then execute this and take a close look at the console, then here, start, and then after a little moment, we get end. Why did we get this little gap here, this little time difference? Well, obviously, because we were mapping 50 million numbers. So the code here really first enters the first iteration, calculates 1 multiplied by 1, then 2 multiplied by 2, 3 multiplied by 3, and up to 50 million. And I don't think it will surprise you that this just takes a little moment for the CPU to execute. And with that, we are already at the definition of blocking code, which in other terms can really just be busy code. So code that is currently executing. And while when looking inside this blocking code function, it all makes sense because we loop over 50 million numbers. If we really just take a look here at this piece of code here in isolation, then it really looks like our code pauses here for a moment. And then after about a second, it will proceed with its end call. But it really doesn't pause. It, of course, just executes the code under the hood. And after that has finished, then it will proceed with the code here. Would be the identical thing as if this code here would be placed inline in the main function. And then it would make absolute sense why the end call isn't printed immediately, but only after having mapped all these 50,000 numbers. That is the first important thing to understand, what blocking code is. In the end, nothing else than busy code. Now coming to the next concept, and that is what a thread is. A thread in the programming world is really nothing else than an independent flow of execution. So if we take a look at our main function, we actually have a flow of execution here, because this function here is called first, then this function is called, and lastly, the print line end is called. So that is one flow of execution, a certain number of functions that are executed in exactly a specific order. And that is the case because by default, a program is running on exactly one thread, which is the so-called main thread. So that means by default, all our programs, instructions, and function calls are executed in order. There are no function calls that can be executed at the same time in any way. No, there is actually exactly one function that is or can be executed at any given time. And with function, I also mean things like multiplying some kind of integer. So that means if on our main thread, on the single default thread, we map and multiply 50 million numbers here, then that means during this operation, our main thread, for example, can't print this end statement here at the same time. So it has to wait for this blocking code to finish until it can print this. However, what now happens if we actually go inside here and we launch a thread? So we put our blocking code inside this thread here instead. And here after this blocking code, we maybe also add a print line statement where we say blocking code finished. If we do that now and we launch this program, then you can see we get start, end, and then our blocking code finished. So this time there was no real delay between start and end. These have been printed pretty much instantly. And then after about a second, the blocking code has also finished. So what has changed now? Well, we've launched our own independent thread. So by putting our blocking code here inside of another thread, so inside of another independent flow of execution, what that has achieved is it has kind of moved this blocking code out of the main execution flow, which means that this code and this code we're still printed in order, but this end println statement here did not have to wait for this blocking code to finish executing. So we now effectively created a completely independent new flow of execution, and that means if we now again put our, well, let's call it thread start in here, thread end, and we now call this once more, and you can see start and thread start blocking code finished and thread end. So what this shows is we have formed an independent flow of execution here inside of this thread, but inside of this thread, our code again is called in order. So first this println statement, then the blocking code, and then the other println statement. Outside of this thread, this is a different thing. So outside of the thread here in this main function, we have another flow of execution. So our main function calls can be executed in a completely different order than the function calls inside of our thread, because we have two independent flows of execution. So while our main function, of course, has to do a tiny call here in order to create this thread and launch it, the actual work that the thread performs inside here in the thread body, that is actually done by the thread itself. And if we have blocking code, so busy code, then that busy code is in the end just blocking the thread it's currently running in. So if we put this in a normal separate thread, then that thread will be blocked, and all calls after that blocking code will simply have to wait for this blocking code to finish, but it does not have any impact on other threads like the main thread, so the main thread can pretty much finish here instantly. So how could this be useful in the real world of programming? Well, on the one hand, multiple threads allow us to execute certain code at the exact same point of time, so in parallel. But this is important to say here. Parallelism in the programming world really means executing something at exactly the same point of time. And this is not the same as concurrency. Because if we think about it, a single CPU core can just execute exactly one instruction at a specific instant. And the only way, therefore, to achieve true parallelism, so for example, to make two mathematical calculations at exactly the same time, that is only possible on devices with multiple CPU cores, which nowadays every modern device has. But a single CPU core can only execute one instruction at a time. So if your machine has, for example, an 8-core CPU, then that means your machine can't execute more than 8 instructions at any given time. And this doesn't apply to your program, this applies to your entire machine. But I can already tell you, on your machine, you will probably have much more threads running at a given time than just the amount of CPU cores. So how could such multi-threading still be useful if there can't be two things executed truly at the same time? Well, the thing is, not every program on your machine is constantly doing and executing a very heavy workload. So it's not like 24/7 your machine is just multiplying numbers here non-stop without any kind of break. But there are actually many different types of tasks where there are idle periods. And in these idle periods, certain programs still have to keep on checking if there's maybe something worth executing. But these checks that happen every now and then aren't that CPU heavy. And that means we can achieve with multiple threads that we have the illusion of executing certain multiple calls in parallel. It's not true parallelism, but we get the illusion because under the hood, multiple threads are just switching between different tasks and different instructions so fast that for us it feels like in parallel. So multi-threading and concurrency is really all about just using idle periods intelligently. So imagine you are at home in your kitchen and you want to cook some rice with chicken. Then if you would cook that rice and chicken on a single thread, you would first cook the rice, and when that rice is finished, you will cook the chicken. However, with multi-threading, you will cook the rice, and while the rice is cooking, where you are kind of in an idle period, you don't have to actually look at the rice, wait for it to finish cooking. No, you can actually do something else while that rice is cooking. So you could prepare the chicken at the same time. And that means overall, you get your dish faster if you stick to multi-threading, because you just use your idle period when you're not busy in a smart way, versus just completely strictly doing everything in order. And in the programming world, what this idle could mean is that, for example, your program is talking to some kind of server, makes a network request. So while making that request and defining how all the HTTP headers need to look like, how the HTTP body needs to look like, how it's actually going to be sent to the server, that's something your program is busy with and needs to actually execute some code for. But the moment the request has been fired and is in transit and reaches the server, where the server processes that request, in that time, your program is actually not so busy. So it can actually speed up that network call processing with more CPU power, because it's completely dependent on how fast the server is with the response. So in that idle period, where your program is waiting for a certain response, it can actually dedicate the time to other tasks. And that means to other threads. And that, of course, also works even if you are running on a single thread. So this as a base lesson around threading and multi-threading. So parallelism is really all about an instruction being executed at exactly the same point of time, which could be due to two threads running on two different CPU cores and executing an instruction at the same time. While concurrency is all about switching between tasks very quickly, which could also technically involve other CPU cores, but doesn't have to. And from that concept of what a thread is, we now move to the concept of what a coroutine is. With coroutines in Kotlin, we very often talk about suspending code. And that is defined via a suspend function in Kotlin, which we can then call suspending code, for example. So let's actually use exactly the same code here in our suspending function, and we just say the println statement is suspending code finished. Now, in order to execute a suspend function, we need to put it in a so-called coroutine scope. And we will take a look at these concepts in a bit more detail later in this video, but let me first of all just execute this here in a coroutine scope that runs on dispatcher's main. And these dispatchers will also get clearer later on in the video, but first of all, let's understand what suspending code is and coroutines. So if we now execute the suspending code in here, because outside the coroutine, you can see it would complain, because suspending code in Kotlin can only be called inside of such a coroutine scope. Let's execute that. Run our program, it says start and suspending code finished. So it seems like everything is just like before when we put this blocking code here inside of an independent thread inside this main function. But let's see what happens if we now take this same code and we duplicate it, and we now launch the app again. Start and suspending code finished. Takes a little moment, and then it says suspending code finished again. However, if we actually put these blocks here in two separate independent threads, we'll replace this with blocking code again. Same thing here for this one, blocking code, and see what this would print, then you can see the blocking code finished at the same time, approximately at least, when putting this blocking code in individual threads. While when putting this inside of a coroutine, it was kind of executed sequentially. That is at least how it seems. So the first suspending code finished println statement was there, and then after 1 to 2 seconds, the second one arrived. Well, why is that? That is because a coroutine is always running inside a thread, and a single thread can therefore host many coroutines. And with this simple example, by launching a coroutine here in coroutine scope dispatcher's main, this effectively means the coroutine and the suspending code in here are launched on the main thread. So on exactly the same thread that this main execution flow is running on here. And this means if we have these two pieces of suspending code, and both pieces each map 50 million numbers on the same thread, then obviously that same thread can still just do one thing at a time. So it can map one number at a time. And just by launching two technically parallel coroutines here, that does not change the fact that our main thread can just handle one thing at a time. And that is actually why it first maps these numbers here in this suspending code, and then it maps those in this suspending code. So what's so special about coroutines? Because right now it really rather seems like a disadvantage. Well, I see coroutines as kind of an upgrade to threading. Coroutines still rely on multi-threading under the hood, but as I mentioned, multiple coroutines and independent execution flows can now happen inside of a single thread. Because the magic thing that coroutines add is this so-called suspend keyword and suspension behavior in general. Because what a coroutine can do is it can actually go inside the suspended state when it's actually reaching some kind of idle period or just executing something that may take a little moment to complete. And in this idle period where a coroutine is in the suspended state, other coroutines that run in the same thread can actually take over. So that's exactly what I mentioned here with the example of your rice and chicken. So you could, for example, have a suspend function here, cook rice, and let's say that takes 3 seconds here for simplicity, and with delay we can suspend a coroutine for a certain amount of time. We have a suspend function, cook chicken. We delay this for, let's say chicken takes a little bit longer, 4 seconds. If we would now execute this in a single execution flow, so on our main thread, for example, here on the main dispatcher, which uses just a single thread under the hood, which is the main thread. And if we now say cook rice and cook chicken, and then we say we're done with the meal maybe, and maybe in between we also say we are done with the rice, and before we say we're starting to cook. And let's remove the start and end here because this is otherwise rather confusing. So what this coroutine does is it uses our main thread under the hood, which obviously has a single execution flow. If we execute this now and take a look here, it says we're starting to cook. Okay, takes a little moment. All right, our main thread finished here, so this can happen. We can fix this by actually waiting for the completion of this. Please don't be confused by what I'm doing right now. But I will call join here. So join will simply say, hey, dear main thread inside of a run blocking block, please wait for this coroutine to finish executing. But I really want to show you this flow inside here. Don't be confused by the rest. We're starting to cook. Then it says we're done with the rice. And then it says we're done with the, why did I say deal? With the dish. We're done with the dish, of course. But what you saw is it first started preparing the rice, took 3 seconds. Then it started to prepare the chicken, which took 4 seconds. And then we were done in a total of 7 seconds. Now, if you're a little bit smart, then, as I mentioned, you will actually cook the rice. And then while the rice is cooking, you can prepare the chicken at the same time. And that in coroutines works with these launch blocks, which is really comparable to what we did with a thread call to launch an independent thread. So we do this here, and we move our print line statement in there, move that one in there. And if we now actually launch this, then it says we're starting to cook, we're done with the rice, and almost immediately afterwards, we're done with the dish because we are effectively cooking the rice and the chicken at the same time. So our total meal now only takes 4 seconds, since in those 4 seconds, we have already had the time in our own idle period to cook the rice. And the interesting part about coroutines now versus threads is that all that code here was still executed on a single execution flow on our main thread, while still being able to kind of achieve this illusion of parallelism again. Because in the end, our functions use this delay function, which is a suspending function, and it pretty much says, hey, we can pause our code here inside this specific coroutine, and while a specific suspend function is actually waiting for something here, for the rice to cook, or for a network call to give us the response, while that is happening, other suspend functions can take over and do work in the same thread, because a coroutine is always running in a specific thread, but we can technically have 10 coroutines all waiting for a network call response inside the same thread, because these coroutines aren't doing anything in that time, and then an 11th coroutine can take over to do some busy CPU work. And this type of behavior is something that coroutines in the end allow us to implement quite easily. However, here the difference that is very important to understand is the difference between a call that still takes a moment to complete but has an idle period, so has a period where the CPU of your device does not actively have to do something, like for example a network call when the server is busy processing the request, then your device, the client device, can do something else, compared to something like mapping 50 million numbers. In that time where your client is doing that, your client device, you can't do anything else, at least on that CPU core, because it's completely busy. And that is why executing the suspending code here in 2 independent coroutines that we had previously here with these coroutine scopes and both running on the main thread, that is why there we first have mapped the first batch of 50 million numbers and then the second one after that. So in that example, we did not really get an advantage in regards to a faster execution, because this code was fully blocking. It was fully requiring the whole CPU core's attention at all the time where we are mapping these numbers. While when actually having a call where we're in an idle period, be it we wait for some kind of file to open and we wait for the disk to respond with something, we wait for a network call because the server is busy with something, here we can absolutely benefit from many, many independent execution flows, and coroutines now allow us to have these independent execution flows even inside a single thread that is technically just one execution flow. I know this is very confusing, but it's exactly like that. But now if you actually recap, having our suspending code that we execute here in these coroutines. So suspending code here, which both have a print line statement. Just as a reminder, if we execute this here and we take a look here in main KT, then suspending code finished, and then our other suspending code finished. So that is definitely executed sequentially here, not finishing at the same time, because both of these calls are blocking code, iterating over 50 million numbers, blah, 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 and both executed on the same thread. However, if we now say something like it dispatches default, and we try this again, then suddenly the code executes almost at the same time. And with that, we come to the next and last concept of this video, which are dispatches and thread pools. So a thread pool is exactly what the name says. It's a pool of multiple threads that can each be reused. So you can really imagine it like a manager in a company where the manager says, oh, okay, this employee is currently not doing a lot. We have a new task, so this employee should do it because they're idle. Well, maybe other employees are very busy with projects, so they may not get a new task. So each employee would be a single thread, and the manager would be the thread pool that also manages each individual thread so that there is an even workload between them. And that is also what coroutine dispatchers here really give us under the hood. So aside from the main dispatcher, we have the default one, and we have the I/O dispatcher. And the only difference that there is between the I/O and default dispatcher is the size of the thread pool they use under the hood. So as I mentioned, coroutine has to run in a specific thread. So multiple coroutines can run in the same thread, but every coroutine has to run in one. And therefore, if we want to truly make use of also parallelism to execute things at exactly the same point of time on multiple CPU cores, then there also must be something in coroutines that allow us to actually have multiple threads in which multiple coroutines again run in. And that is what the dispatchers manage. Specifically, with the I/O dispatcher, there is a thread pool behind the scenes that the dispatcher manages that can go up to 64 different threads. While with the default dispatcher, it only gives us up to as many threads as we have CPU cores on our device. So why is that? Why have these dispatchers been chosen like that? And let's first of all understand what these are even good for. The default dispatcher is recommended for CPU-heavy work. CPU-heavy work would be something like iterating over 50 million numbers, making a very large state update in a mobile app, maybe compressing a bitmap because then your code has to iterate over every single pixel and apply some kind of compression algorithm. So something where the CPU is just busy all the time when executing that code. That would be code that is ideally executed on the default dispatcher. While the I/O dispatcher, as the name says, in and out, is better for I/O-related calls. Reading a file, writing to a file, making a network call. In other words, code where your code will have idle periods, where your code can't actively make the code execute faster by just using more CPU power. Because again, if you're waiting for a server's response, you can have as big of a CPU as you want, the server won't reply faster. And that is a difference, because if we think about it, if we have such blocking code, let's say again, we want to map 50 million numbers, and we not only want to map that once, but maybe many, many times, let's say 50 times, then if our device has, let's say, 10 CPU cores, there really isn't any benefit in using more than 10 threads if we have 10 CPU cores. Because as you've learned, every CPU core can still just achieve one single thing at a given time. So every CPU core can just multiply one number at a given time. If we then have multiple threads, and therefore technically also multiple coroutines on a single CPU core, then executing such blocking code, such busy code, won't be any faster. So that is why the default dispatcher gives you a pool of as many threads, of up to as many threads as you have CPU cores, because that is the full workload kind of, which is completely optimized, therefore, to execute as many instructions as possible in a given time, while the I/O dispatcher gives us a thread pool of up to 64 threads. Because on the I/O dispatcher, we expect to have much, much more of these idle periods where we are waiting for a network call. Let's say we are making 50 network calls at the same time. Then making that call from the client and sending our request to the server is something that is reasonably simple and fast. But as I mentioned, the delay comes from the network traffic, from the latency, from the server processing the request. So while each of these calls takes a moment to complete, the actual CPU is not so busy when making network calls, and therefore we can use many, many threads at the same time with the I/O dispatcher, make many, many network calls, read from many, many files at once, because here we really benefit from this fast switching between threads in order to really use our time and structure our instructions intelligently. And that's really the whole difference between I/O and default dispatchers. In the end, the dispatcher just takes a look under the hood. Okay, here I have 64 threads. New coroutine is launched. Let's take a look at which of these 64 threads is currently idle. Let's execute the coroutine on that one. And now with coroutines, the difference is you could technically have 10,000 coroutines that are all executed on a set of 64 threads. And these coroutines can then again switch among each other when some are idle, when some are busy, to just have a smart way of organizing work. That is really what all this is about. And that also means if you have such a suspend function, and that is the big reason why this is actually grayed out here, because we don't have any suspending code inside this suspending code function. That is why here at this point, we should actually say with context, dispatcher's default, because that is exactly the thread pool that we want to execute this blocking code on, because that way we actually just switch to a different thread pool here when executing the suspending code. Now it's not grayed out anymore. so that even if we would accidentally call this code here from the main dispatcher, from the main thread, the code itself would make sure that it launches on the right thread pool and can't accidentally block anything important like our UI, which the main thread is most responsible for. And that is another big advantage of coroutines over threads, that coroutines can actually switch the context they're running in. So you can just say, okay, this part of the code runs on the default dispatcher because it's CPU heavy, then another part of the code actually runs on the IO dispatcher because it's making a network call. But all in all, this is really what this whole concurrency, threading, coroutines thing is all about. Super short recap. A thread is an independent flow of execution. There are many threads running at the same time on your machine, just so that all the programs that are currently active on your machine can intelligently switch between tasks, so that you have the illusion of things happening at the same time, even though only a very small amount of things can truly happen at the same time. Then we've talked about things like parallelism, which is really about true execution at the same time. We've talked about concurrency, which is just about executing tasks in a smart way, so cooking rice and chicken at the same time versus cooking rice first and then chicken, because just by arranging your tasks and your instructions in a smart way, you can already achieve a certain result faster, very often at least. Multithreading is therefore just about using multiple threads, as the name says. And then we have coroutines, which use suspending code. Suspending code means it can actually pause and resume at certain breakpoints, which are these suspending calls like delay or the suspend function here itself. Multiple coroutines can run inside of a single thread and can therefore distribute work for that single thread among each other. However, if we execute blocking code inside of a coroutine, like here for example, then that will still make a certain thread under the hood busy. And if that whole thread is busy that many coroutines are running in, then all of these coroutines won't be able to do work until that thread is not busy anymore. I hope that all made sense. If you want to really dig deeper into this topic of coroutines, I'll link my Kotlin Coroutines and Flows Masterclass course below, where this would really just be one out of, I think, 40, 50 lectures. So if you say I'm serious about Kotlin, then that is something you should learn. Thanks for watching. Have an amazing rest of your week. See you back in the next video. Bye bye.